So picking up from yesterday where we were looking for absolute extrema, and maybe we were starting to talk about local extrema as well. That's exactly what we're going to do now. So we got a little bit more complicated function than the one we dealt with last time. We've got 1 over the square root of 9 minus x squared, which you may or may not know exactly what that looks like, what the graph of that looks like. Even if you don't, that's okay, because we should be able to still find any absolute extrema on it. So the first thing you normally want to do whenever you're asked to find maxima or minima or extrema, whether it's local or it's absolute, you want to look for the domain of your function. So first off, what's the domain of our function? How do we find that domain?
We know that it can't be 1 over 0, so we look at when the denominator can get to 0.
Okay, so we can't let this denominator, the square root of 9 minus x squared, it cannot equal 0. And also, it's got a square root in it, right? So in addition to that, the thing inside the square root has to be
Positive,
right? 9 minus x squared has got to be greater than 0. And I think if we, 9 minus x squared, the square root of 9 minus x squared not being 0, that falls into the same category of this, right? 9 minus x squared, it has to be greater than 0. The only way that the square root of 9 minus x squared would equal 0 would be if 9 minus x squared equals 0, and so this is taking care of that also. So all we have to do is solve this inequality, giving us x squared is less than 9, or x is less than 3 greater than negative 3. Everybody okay with that?
Yes.
Okay, so we got our domain. So now as we go through here and look for these extreme values, we know that they have to fall within this boundary. They have to be between -3 and 3. And so what we did was we said, all right, endpoints, and we said critical values are the only places where we might have extrema. Does this function have any endpoints? Just looking at the domain.
No, right?
No, this does not have any endpoints, right? Because these are open intervals. This is the open interval from -3 to 3. We get very close to -3, but we don't ever get there. We get very close to 3, but we don't ever get to 3. Right, so this is an open interval, no endpoint. So we don't have to worry about this time. That's nice. All we have to worry about is critical values, which means we need to figure out when the derivative is
0 and undefined.
0 and undefined, exactly. So in order to figure out when the derivative is 0 and when the derivative is undefined, we probably need to figure out what the derivative is. So f of x, which we had written as 1 over root 9 minus x squared, could also be written as 9 minus x squared to the -1/2 power, right? If we just wrote that as a power. I think that makes the derivative a little bit easier to find, because now this is just u to the -1/2 with u equal to 9 minus x squared. And so the derivative ought to be -1/2 of u to the -3/2 times the derivative of u, which is -2x. Everybody okay with that so far? Okay. And we got the negatives, which will cancel, and then a 2 in the numerator and a 2 in the denominator, which will cancel. So all I'm really left with is an x in the numerator, and then this 9 minus x squared to the -3/2 can drop down to my denominator as a 9 minus x squared to the +3/2. Everybody okay with that being our derivative?
Yes.
Yeah.
Wonderful. All right, so we got our derivative. Now we need to see, when does it equal 0? So when does a fraction equal 0? Only if the
numerator is 0,
which
and
would
the
tell us
denominator isn't 0.
right, the numerator is 0 and the denominator isn't. So if x is 0, this numerator is 0, and the denominator 9 minus 0 to the 3/2 is definitely not 0. True. So x equals 0. This is one critical value. And then we also need to see when this is undefined. And so it's undefined when the denominator is equal to 0. And well, that would just, the 3/2 power, if I were to, this is a cubed and a square root. So if I were to square it and cube root the 0, that still stays as a 0. So we just get 9 minus x squared equals 0, which would give us x equals plus or minus 3, which would be critical values if they were in the domain. But these are not in the domain, and so we can ignore those. Everybody okay with ignoring those because they're not in the domain?
Yeah, makes sense.
All right, cool. So then all we've got here is x equals 0 is our only critical value, which means we're not going to have an absolute max and an absolute min. We're just going to have one or the other of them, most likely. And from there, let's first off figure out what f of 0 is. What's f of 0?
One-third.
Should be just 1/3, yep. And how would we determine if that's an absolute or a local max or an absolute or local min? Or potentially neither. Any ideas on how we might do that? How do we get a local max or a local min? What has to happen to our function? All right, let me sketch a graph here. Here's a graph of a function. See it over there? How did I get a local or an absolute maximum on this? What did my function do? It went from,
Direction.
right, it changed direction. It went from increasing to decreasing, didn't it? Or potentially it might go from decreasing to increasing. True?
Yes.
All right, so let's think back to when we were graphing our derivatives, and what did we determine about the derivative and what the derivative could tell us about whether the function was increasing or decreasing?
When it's negative, the function is decreasing, and when it's positive, the function is increasing.
All right, so if f prime was negative, f decreased, and if f prime was positive, f increased. You guys all remember that? Now that somebody out there said that. So here is x equals 0. And let's see what happens between -3 and 0 and between 0 and 3 to our derivative. So what I'm making here is called a sine chart. Okay? A sine chart is going to indicate to us whether the derivative is positive or negative on each of these intervals, so we can see how the function itself behaves. So if I were to take a number between 0 and 3, what's a number between 0 and 3 you like? Take anything.
1.
1, that's a good one. All right. If I were to plug 1 into my derivative right here, do I get a positive or a negative number? So the numerator would be 1, which is definitely a positive, right? And then we're going to divide that by, let's see, 9 minus 1 is 8, that's positive. And the square root of 8 is positive, and the square root of 8, which is positive, cubed is still positive. So we'll have a positive number divided by a positive number, which gives us a
Positive number.
positive number. So our derivative is positive, telling us that f is increasing. Everybody good with that?
Yeah.
Okay. What happens if we take a number between -3 and 0, like let's say -1? We end up with a negative in the numerator, right? Divided by -1 squared is still 1. 9 minus 1 is still 8. The square root of 8 is still positive, and that positive cubed is still positive. So we end up with a negative number, which tells us, since the derivative is negative, that f is decreasing. Everybody good with that?
How'd you get the negative in the numerator if it's just, oh wait, no, I figured it out.
Right, just x, so we put a negative number into it. So.
Yeah.
Everybody good there?
Yep.
So what does that tell us about this value, f of 0, which is 1/3?
It's a minimum.
It's a minimum. And is it just a local minimum, or is it local and an absolute minimum?
The second thing.
The second, yes, local and absolute. And we know that because our function, other than at 0, is always decreasing from the left towards that x equals 0 value, and then it's always increasing again after that x equals 0 value. Does that make sense to everybody?
Yeah.
Wonderful. All right. Here's what we're going to do. Real quickly, I'm just going to pull up Desmos because everybody loves Desmos, right? We'll look at the graph. It's 1 over the square root of 9 minus x squared, right? And here's the graph. You can see probably pretty clearly that it is definitely decreasing, and it's slowly decreasing after about -2.9. Starts slowly decreasing till it gets to that value at x equals 0, which you can see is 0.333 according to Desmos, 1/3, which is what we got. Then it starts increasing again afterwards, and then it starts increasing very rapidly as it gets towards the vertical asymptote at x equals 3. So pretty cool, really, that without knowing what this graph looked like, we had a general idea of what its graph should look like. We knew that it should decrease from -3 to 0, hit a local and absolute minimum of 1/3 at x equals 0, and then start increasing again after that towards the vertical asymptotes at -3 and 3. Good or no?
Good.
Wonderful. All right. Now, next and also very important thing is we need to recognize that when we find these critical points or we find these endpoints that we think might be maxima or minima, they are not always maxima or minima. So just because you get a critical value does not guarantee that it will be a local or an absolute max or a local or an absolute min. It might be one or the other, or it might be both, or it might be neither. So we got to be careful about that. We're going to quickly illustrate that with 2 little examples here. Let's take a look first at y equals x cubed, and we're going to find all the extrema of it. Now, if you think about that, you know what y equals x cubed looks like, right? Hopefully. Right, looks like a cubic. What's the local and absolute max of this?
None.
There aren't any, right? There's no local max. There's no local min. There's no absolute max. There's no absolute min. It's going down to -infinity and up to infinity. And there are no little turning points in it. It does have this place where it flattens out, right, at the origin, but it doesn't go up and back down. It doesn't hit a local max. It just sort of flattens out there. So when we go through and do this, we should show that no matter where we find a critical value on this, it's still not an extreme. So let's find the critical values by taking the derivative. Y prime is 3x squared. And we know that this is never undefined, right? 3x squared is always defined. And that y prime equals 0 if 3x squared equals 0 or x equals 0. And so we know that this is our only critical value, right? This is our critical value because it's the only place where the derivative is 0 or the derivative is undefined. And it's the only place where this function might have a local or absolute max or min, even though we know that it doesn't. And so if we go in and put 0 on a sine chart here, a sine chart of y prime here, since we use y, sine chart for y prime, I'll go ahead and take a positive number and plug it into your derivative, right? Here's our derivative. Take a positive and plug it in. What do you get? Positive or negative?
Positive.
You get positive, right? Which tells us that y is increasing. And what about if you plug in a negative number to it?
Positive.
Still get a positive, right? You square that negative, becomes positive, multiply it by 3, it's still positive. So this is telling us that no matter what, this function is always increasing. And therefore, it's not going to have a local max or a local min at 0, even though it was a critical value, right? We don't have increasing and then decreasing or decreasing and then increasing. Everybody good with that?
Yeah.
Yep.
All right, cool. Let's do cube root of x. So this one you may not know what it looks like, and that's okay. I mean, it's not really okay, but we'll pretend it's okay if you don't know what that looks like. Let's find the derivative. And this is x to the 1/3, so the derivative is 1/3 x to the negative 2/3. Or we could write that as 1/3 x to the 2/3. So when does a fraction equal 0? When does y prime equal 0? Only if
Never.
it's good.
If
Like
the
this one would
numerator
never
is
equal 0.
Which it can't.
Right, this one can't because the numerator would have to be 0. So we can say y prime is never 0. But when is y prime undefined? Well, when the denominator equals 0, right? So if 3x to the 2/3 equals 0, which would be x equals what?
0.
0. Exactly. And so we have one critical value. This is our critical value. And we want to make a sine chart to see if this is an extrema or not. So our sine chart for y prime should show us when we plug in a positive number to our derivative, right? This is our derivative. If we plug in a positive, the numerator is positive, and the denominator, when we plug in a positive number and cube root it, we get a positive, and square it, we get a positive, and multiply it by 3, it stays positive. So this is positive, and y is increasing. What about when we plug in a negative? The numerator is still positive. The denominator, when I cube root a negative, stays negative. And then when I square that negative, it becomes positive times another positive is still positive. So we find that y is increasing and there are no extrema on x to the 1/3, or the cube root of x. And we can see that if we were to look at the graph, x to the 1/3 is just sort of the, it's the inverse function of the cubic function, right? It's just turned on its side, reflected over y equals x. And there are no local max or local min or absolute max or absolute min. It increases forever and it gets smaller forever over here. The function is always increasing from negative infinity to infinity. Good or no?
Good.
Anybody have any questions on any of this so far? Okay, so this, what I've got up here now, is what we've been talking about. And so we're going to practice this with some nice, simple, easy functions for a little bit, and then we're going to move into some more complicated functions, some piecewise functions, and some really ugly looking functions that are going to require us to actually do some thinking. So we talk about a function increasing, like we already said, a function increases on an interval if the derivative is positive, and a function decreases on an interval if its derivative is negative on that interval. Okay, so we should already know the answer to the question given to us, but we want to, using some calculus and some algebra here, show when the function x squared is rising and when it's falling. So when it's increasing and when it's decreasing. Okay. So how should we go about doing that? What's the first thing we need to do?
Find the derivative.
Find the derivative. And for like the next week or so, generally when I ask you what's the first thing we should do, most of the time the answer is going to be take a derivative. So for those of you that don't like to participate, it's pretty much a safe bet if I ask you what should we do first, probably take the derivative. So what's the derivative of x squared?
2x.
2x.
2x, easy, right? And when does that equal 0?
At 0.
When x is 0. And when is f prime undefined?
Never.
Exactly. So on our sine chart, we just have the value of 0. And if we plug in a positive number into our derivative, do we get a positive or a negative?
Positive.
We get a positive, right? And if we plug in a negative number, what do we get?
Negative.
Negative. And we see that we have a minimum at x equals 0, right? And we have a function that is decreasing from negative infinity to 0, and a function that is increasing from 0 to infinity. Give me 1 second, then I got something else I got to talk about this. But give me a second here. Okay, sorry about that. All right, so a very, very important thing that I need to talk to you about on this page here is the use of parentheses and brackets when we're talking about increasing and decreasing intervals. So before I go on my little rant about this here, I have to ask this important question. Do any of your parents work for the College Board? No? Okay, good. All right. The College Board, read the sarcasm into this, in their infinite wisdom, thinks that when you define increasing and decreasing intervals for real number values, you should put them into brackets, even though that's stupid. Okay? This is telling us that this function decreases from negative infinity to 0, including at 0. So it's decreasing at 0. And then it is also increasing at 0 from 0 to infinity. Every math teacher I've ever had, every competent math person that I've ever spoken to agrees with me that these should be parentheses, but the College Board wants you to indicate increasing and decreasing intervals using brackets, which makes absolutely no sense because you can't be both increasing and decreasing a specific number. That's where we're changing from increasing to decreasing. We're doing neither at that point. But for our purposes, for the AP test, you have to put the real number values in brackets. The infinities can stay in parentheses, but any real number values for increasing and decreasing intervals have to be in brackets. Good?
Good.
I mean, not good because it doesn't make any sense, but good that you have to do it and understand that's what you're doing. All right, cool. Let's do another nice little easy one here. We want to figure out when is this function x cubed minus 4x increasing and when is it decreasing? You guys think you could do this one on your own or no?
Yeah.
All right, I'll give you guys about a minute or two here to try and work through this one, and then we'll work it out together afterwards. Ready, go. What's the first thing we should do?
Find the derivative.
All right, so what is f prime of x?
3x squared minus 4.
Perfect, 3x squared minus 4. We know this is never undefined as we search for our critical values, but it does equal 0. Let's see, that'd be add the 4 and divide by 3, that'd be x squared is 4/3, right? Or x equals plus or minus the square root of 4/3, which would be 2 over root 3. Everybody good with that so far? And we'll make a sine chart. So what's a nice easy number to plug in to our derivative that's between negative 2 over root 3 and positive 2 over root 3?
0.
0, right? 3 times 0 squared is 0, minus the 4 gives you a negative, which tells you that between here, this function is decreasing. Good?
Good.
Okay.
Yeah.
Plug in something more than 2 over root 3. Now, that should be pretty easy to figure out something more than that. You don't need something really close to 2 over root 3. You just need any number that's more than that. So I'm going to pick like 1,000,000. If I take 1,000,000 and square it and multiply by 3 and then subtract 4, I ought to get a positive number, right? Which tells us that this function is increasing. Everybody agree with that?
Yeah.
Okay. And what happens if I plug in, let's say, negative 1,000,000? When I square that, it's a very large positive times 3, which is still a very large positive. Subtract 4, still positive. So our function is increasing from negative infinity to negative 2 over root 3 with a bracket, union 2 over root 3 with a bracket to infinity with a parenthesis. And it is decreasing on the interval negative 2 over root 3 to positive 2 over root 3, both with brackets. And this is how I want your answer to be written. Good or no?
Good.
Wonderful. All right. So using this same idea, what could you tell me is going on here at negative 2 over root 3? We're having our function has a
Local maximum.
local max, and at 2 over root 3, our function has a local minimum, right? So anytime our function goes from from increasing to decreasing, we get the local max, and anytime it goes from decreasing to increasing, we get the local min, which tells us that anytime our derivative goes from positive to negative, we get the local max, and anytime our derivative goes from negative to positive, we get the local min. And so that's what I've got written here. If our derivative changes signs, positive to negative, we get a local max. And if our derivative changes signs, negative to positive, we get a local min. And in some cases, if it doesn't change signs at that critical value, there's no local extrema at that critical value. And we saw that with x cubed and the cube root of x when we did those ones a few minutes ago, right? And in addition to that, we can have local maxes and local mins at endpoints. You know, I think those are pretty self-explanatory. That's a local min at my endpoint, and that's a local max at my left endpoint, or a local max or a local min at my right endpoint, just so long as the function increases to the left or increases to the right and decreases to the right of a left endpoint, or if the function is increasing towards a right endpoint or decreasing towards a right endpoint. That will give you a local max or local min. Make sense or no?
Yeah, makes sense.
Perfect. Okay. So let's see if we can use these derivative tests to find all the local extrema and to identify which of those extrema might be absolute extrema also. Okay, so we're going to start with a nice easy one, x cubed minus 12x minus 5. What's the first thing we should do?
Find the derivative.
Wonderful. All right. F prime of x should be what?
3x squared minus 12.
Excellent. Is that ever undefined?
No.
What?
No.
No, never undefined. Okay. And what about equaling 0?
Positive or negative 2.
Positive or negative 2, right? Okay. So what values? These are our critical values, right? And so those are the only two values that need to go onto our sine chart, negative 2 and 2 for the derivative. And what's a nice easy number between negative 2 and 2 to plug in?
0.
0. If I plug in 0 to my derivative, I get a negative. Right? If I plug in a positive number greater than 2 to my derivative, like a million squared times 3 minus 12 is positive. And suppose I plug in something like negative a million, well, that's going to give me also a positive. Everybody good there? Or no?
Good.
Great. So it looks like we have a local max at negative 2 and a local min at 2. Let's first, before we worry about if they're absolute extrema, let's find the values of the function of each of those numbers. So f of negative 2, well, that's negative 8 plus 24 is 16. Minus 5 would be 11. And then plug in 2, that's 8 minus 24 is negative 16. Minus 5 is negative 21. And we know they're local for sure, but how would we determine if they are absolute extrema? We need to check our in behavior, because if we look at our sine chart, we know that we get down here to negative 21, right, at a local min, and then we start increasing. And if this increases forever towards infinity, then it's certainly going to go above this local max. And if this is decreasing to the left forever towards negative infinity, it's certainly going to eventually go below negative 21, right? So we're going to see if perhaps maybe this doesn't increase towards infinity, maybe it increases towards an asymptote or something. So we have to check the in behavior by looking at the limit as x approaches infinity of our function, and the limit as x approaches negative infinity of our function. So what's the limit as x goes to infinity of f of x?
Positive infinity.
Positive infinity, exactly. So this is increasing without bound. It's definitely going to go above 11. So this is not an absolute max, it's just a local max. And what about with negative infinity? When I cube that negative infinity, that becomes a very, very large negative number, right? And the negative 12x and the minus 5 aren't enough to cancel out the cubed. And so what do we end up with?
Negative infinity.
Should be negative infinity, which tells us that we're decreasing without bound. We're going down to huge negatives and definitely going below negative 21. So we would just say we have a local max of 11 at x equals negative 2. And we'd say we have a local min of negative 21 at x equals positive 2. And we would say no absolute max or min. Everybody good with that?
Do you have to go through and do the and like find the limits in the end behavior if you can already see like from it the sine chart that it goes like to both infinities?
So yes, you need to, unless you know without a fact or like without any doubt for sure that it's going to go towards negative infinity and to up towards infinity. So like for a cubic, you know that on one side a cubic always goes to infinity, on the other side it always goes to negative infinity. That would be okay. But for other functions where you may not be as familiar with what they look like, you definitely can't just count on the sine chart saying increasing or decreasing to guarantee it. You got to make sure it's not approaching an asymptote there. Like, if you had a rational function in there, it might be increasing forever, but it might be increasing towards an asymptote of y equals 1 or something. So it's never going to go above 1. Does that make sense?
Okay, thank you.
Yeah. So, for something like this, you probably don't know right off the bat what x squared minus 3 times e to the x looks like. I'm guessing most of you don't know what that graph looks like. Would that be accurate? Yeah. I feel like that would be accurate. So in this case, it may look like we have no absolute max or min, but we may have one. We'll have to see. Maybe I'm just, saying something that's not really the case, but we'll find out. So we want to find the extrema and see if any of them are absolute extrema. What's the first step?
Find the derivative.
Wonderful. Find the derivative. So this derivative is a little bit more difficult to take, but not that bad. It's just a product of two functions, right? So we'll use the product rule. So it should be first function, x squared minus 3, times the derivative of e to the x, which is e to the x, and then plus second function, which is e to the x, times derivative of x squared minus 3, which is 2x. Everybody good with that being the derivative?
Yeah.
Cool. All right. Well, that's a little bit messy, so it'd be nice to factor out any common terms. What's the common term in those?
E to the x.
Wonderful. E to the x. From the first one, we have x squared minus 3, and from the second one, we have plus 2x. I could factor that a little bit further, right? E to the x times, what does that become? X plus and x minus, right? For the minus 3, what should it be?
Plus 3 minus 1.
Plus 3 minus 1. Perfect. Everybody agree with that?
Yeah.
Okay, cool. So, first off, when is this undefined?
Never.
It is never undefined. Okay, definitely true. I can take any number and do e to that power, right? That's just a number. And any number plus 3 is just a number, and any number minus 1 is just a number, and you can take any 3 numbers and multiply them together. So never undefined. But it does equal 0 if any of these 3 pieces equals 0, right? So e to the x equals 0, or x plus 3 equals 0, or x minus 1 equals 0. True?
Yes.
Yeah.
All right, so this one's x equals 1, this one's x equals negative 3. Those ones are pretty easy. You learned how to do those in like 3rd grade. What about e to the x equals 0?
There's no value.
0.
Yeah, this one is never, right? Anytime I take something and raise it to a power, I will always get some positive number, unless I'm taking 0 to a power. That's 0 to a power is the only way to get 0, and e is not 0, so this will never be true. So we have 2 critical values, negative 3 and positive 1. So we'll make our sine chart. What's the nice easy number between negative 3 and 1 that we could plug in?
0.
0. So plug in your 0. E to the 0 is positive, right? So that's a positive. 0 plus 3 is positive. And 0 minus 1 is negative. So we got a positive times a negative gives us a negative, right? What about greater than 1? Something nice and easy, greater than 1, like a million. That'd be positive. X plus 3 would be positive. And x minus 1 would be positive. So 3 positives gives us a positive. And what about something less than negative 3? Something nice and easy, like negative a million. Now, e to the negative a million is just 1 over e to the million, right? Which is just a very, 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 very small positive number, but still positive. So positive times negative should give us a positive. Everybody good with that or no?
Good.
Okay. Let's find the values of our function at -3 and at 1, because that's at least a local max and a local min, and perhaps one of them or both of them might be absolute extreme also. We'll have to figure that out. So what's f of -3? -3 squared is 9, right? Minus 3 is 6. So 6e to the -3rd power. And what about if I plug in 1? That's 1 squared is 1, minus 3 is -2, times e to the first, so -2e. Everybody good with that?
Yeah.
All right, cool. Now let's look at what happens as x goes towards infinity on our original function. So what's the limit as x approaches infinity of f of x? Because it would appear that we hit this, minimum here at 1, and then we increase, right? We increase forever. Well, if this increases towards infinity, then this maximum, we're going to clearly go way past 6e to the -3 eventually. But if it doesn't go towards infinity, if it approaches some other number like 5 or -1 or something like that, maybe this is the absolute max. So what happens when we plug in very, very large numbers to our original function? We get a very, very large number squared, which is still a very, very large number, right? And subtract 3 from that, that's still infinite. And you multiply it by e to the infinity, which is also huge. What do you end up with?
Infinity.
Infinity. So we know that as x gets larger, our function increases without bounds. So we're going to go way past 6e to the -3 if we're going towards infinity. So definitely this is just a local max at x equals -3, not an absolute max. What about the limit as x approaches negative infinity of our function? Effectively, that's going to give us negative infinity squared, right? An infinity squared, let's say, right? Because negative infinity squared is the same as infinity squared, minus a 3. That -3 is probably pretty insignificant there. Would you guys agree with that?
Yeah.
Yeah. And then we're going to divide that by, well, e to the negative infinity, right? That drops to the denominator, e to the infinity. So if the numerator of a fraction gets bigger more quickly than the denominator of a fraction does, this should go towards infinity. But if the denominator of a fraction is getting bigger faster than the numerator, it should be going towards
0.
0. So which is happening? Is the numerator or the denominator getting bigger more quickly as we put in very, very large numbers?
Denominator?
Yeah, the denominator is an exponential function will always increase more rapidly than a polynomial function, right? This is just something squared. Even if we put in, I'm just going to go to Desmos real quick here. Even if we put in like a relatively large number, it doesn't even have to be that big. I mean, pick something like 10. right? We know what 10 squared is, right? 10 squared is 100.
Yes.
And if I try to do e to the 10th power, well, that's already 22,000. It's already, I mean, that fraction has already become 100 over 22,000. It's already pretty darn close to 0. And suppose I made that, you know, the 100th power, let's say. 100 squared is 10,000, and now we've got 10,000 divided by, you know, 2.6 times 10 to the 43rd power. So clearly that exponential is going to increase far more rapidly than our polynomial function. So this should be going towards 0. So what that's telling me is that I have a horizontal asymptote, right? Y equals 0 to the left. So what's happening here is my function is, as I go towards negative infinity, it's actually looking more like this. It's decreasing forever, but it's not decreasing without bound. It's decreasing towards 0, which means, is it ever going to go back below negative 2e?
No.
Nope. So if I'm going to start going up, right? This is my increasing, but I'm increasing starting above 0 up to my local max, down to this local min of negative 2e, and then increasing again. So that negative 2e value should be an absolute minimum. Does that make sense to everybody?
Yeah.
All right, so we have a local max of 6e to the negative 3, and that was at x equals negative 3. And we have a local and absolute min of negative 2e. And what was that? That was at x equals 1, right? And we have no absolute max. Everybody all right with that?
Yep.
Cool. And real quickly, just for the heck of it, what was our original function? It was x squared minus 3, right? Times e to the x. And if we look at the graph of this, we can see that's exactly what's happening here, right? To the left, we've got a horizontal asymptote at y equals 0. So we're increasing towards this local max at negative 3, which is, you know, 0.299. I guess that's 6e to the negative 3. And then we drop down here to our local min at 1, negative 2e. And then we start increasing again after that. Good or no?
Good.
All right. Anybody have any questions before we add some more fun stuff into this for the last 15 minutes here? Okay. Let's take a look at a piecewise defined function. So we want to find the extrema of f of x if f of x is 5 minus 2x squared for x less than or equal to 1, and x plus 2 if x is greater than 1. So what's the first thing we need to do?
Find the derivative.
Wonderful. I was going to say the answer is still the same. Still find the derivative, but this time it's a little more complicated because I have two different functions that define f of x, right, for different domain restrictions. So we will say that if x is less than or equal to 1, f prime of x is the derivative of that, right, which is
negative 4x.
all right. And we'll say that if x is greater than 1, what is f prime of x?
One.
1. All right. So now this should make it pretty straightforward for us to find any critical values here. Let's go in and say, when does f prime for x less than or equal to 1? Undefined? Ever or no?
No, it's never.
Yep, never undefined. And when does it equal 0? If
X equals 0.
x equals 0. And we'll check and make sure, is x equals 0 within that restriction?
Yes.
No.
Yes, it is. So this is a critical value. Suppose our restriction had been x is greater than or equal to 1, and we came out with x equals 0. Well, then it would not be within that piece of the domain, so we would ignore that value. That makes sense to everybody? Yes, no, maybe?
Yes.
Okay. What about the number 1? Is 1 ever undefined?
No.
Nope, never undefined. And does it ever equal 0? Does 1 ever equal 0?
No.
Nope. So no critical values from that. So we only have one critical value for this, x equals 0 at the moment. But where else do you think we should be sort of investigating what's going on?
At the junction between the two pieces.
Exactly, because one of these is linear and the other one is parabolic. And if I have something, I mean, I'm just going to sort of say, oh, there's my parabolic, right? And then perhaps I have a linear thing coming off of it. Well, this is like a corner or a cusp type thing going on there, isn't it? And we need to remember that f prime, the derivative, is undefined if there is a corner, if there is a cusp, if there is a vertical tangent, or if there is a discontinuity. Okay. So we need to check and see if any of those things are happening at x equals 1, where the two pieces of our piecewise function meet up, and see if the derivative is undefined there. Because if the derivative is undefined at 1, then that's a critical value that we need to be interested in as well. Everybody good with that?
Yep.
So the question is then, how do we do that?
Take the limit as they approach 1.
Okay, so that's the start, right? Let's take a look at what happens from the left and from the right. So the limit as x approaches 1 from the left of f of x is what?
3.
3. And what about the limit as x approaches 1 from the right of f of x? That'd be from the x plus 2 part, right?
Also 3.
Also 3. So we've eliminated discontinuity, right? If the limit from the left is equal to the limit from the right, and the function is defined there, right? Less than or equal to 1. There's no discontinuity, so we can eliminate that. Then, what about a corner or a cusp? We would know those if the derivative from the left and the derivative from the right were equal to each other or not. So what's the derivative from the left at 1?
-4.
It's definitely -4, right? -4 times 1. And the derivative from the right is
Just 1.
just 1. Those are not equal. The derivatives from the left and the right are not the same, which tells us that we've got something weird going on there, a corner or a cusp type thing, which tells us that f prime is undefined at x equals 1. So this is another critical value. So now we're going to need a sine chart with the values of 0 and 1 on it for our derivative. So unfortunately, this time we can't plug in 0. So where do you guys want to start? Where do we want to start with this?
Can we just start from like the very left when it's less than 0?
Sure. Yep. Let's start with the negative value. So let's plug in negative, I don't know, negative 1,000,000. Where do I plug in negative 1,000,000 into? Which derivative? This one or this one?
The
Negative
first one.
4x.
First one, right? Negative 4 times negative 1,000,000 is positive, right? What about something between 0 and 1, like a half? That should still go into this one, right? Gives me a
Negative.
gives us a negative, so decreasing. And plug in something more than 1. We got to plug that one into this derivative. Any number you plug in that's more than 1, like 1,000, gives you 1, right? So positive. And so we know we're increasing after that. So I want you guys to figure out what f of 0 is, figure out what f of 1 is, and then write out your extrema. And I'll be back in 1 second. Okay, sorry about that. My 7-year-old sliced his finger open on an aluminum can and had to, wipe up the pools of blood. All right, so we've got our local max. What'd you guys get for your local max? What was f of 0?
5.
Okay. Local max of 5 at x equals 0, and a local min of what?
3.
F of 1 was 3, so a local min of 3 at x equals 1. And were any of these absolute extrema or no?
No.
Yep, this is going towards infinity, and this is going down towards negative infinity. And so we have no absolute max or min. Everybody good with that or no? Any questions? We got one more problem to do. We may end up going just a minute over. I'll try not to though. Everyone's good? All right, let's take a look at the natural log of the absolute value of x over 1 plus x squared. What should we do first?
Take derivative.
You're right, a derivative. Okay, so that's a problem because we haven't taken derivatives with anything that has an absolute value in it yet, have we?
No, we haven't.
No, I don't think we have. So we got to think a little bit about how to get rid of that absolute value. So we could rewrite this as a piecewise function, Well, looking at the domain of this and seeing what happens when we choose negative numbers and positive numbers. So first off, let's find the domain. The only thing that we couldn't have inside of this natural log would be a 0, right? We normally can't have a negative, but the absolute value fixes that problem. So as long as the thing inside of here, x over 1 plus x squared, doesn't equal 0, it's in the domain. So that'd be if x equals 0, right? So we can't have a value of x equals 0. Everybody agree with that?
Yes.
Okay. So say x cannot be 0. What happens if x is positive? If x is greater than 0, what can you tell me about x over 1 plus x squared?
It's positive.
Positive. And if x is less than 0, what can you tell me about x over 1 plus x squared?
It's negative.
Negative, right? Because the 1 plus x squared is always positive no matter what. And then put in a positive, that makes the numerator positive. Put in a negative, it makes the numerator negative. Okay. Hold on one second. Back. Okay, so what we're going to do, because we know that when we take the absolute value of a positive, what do you get? You get the same thing that you started with, right? And if you take the absolute value of a negative, you get the opposite of what you started with. So really, this function should look like natural log of x over 1 plus x squared without the absolute value, if x is greater than 0, and natural log of the opposite of that, if x is less than 0. And we're not too concerned about x equaling 0, right? Because we know that's not in our domain. True?
True.
All right, so now we're finally ready to take our derivative. So our derivative, if x is greater than 0, f prime of x, well, let's see, it's natural log of x over 1 plus x squared. So to take the derivative of natural log of u, it should be 1 over u times the derivative of u, and that's the derivative of this x over 1 plus x squared, which we have to use the quotient rule for. So 1 plus x squared times 1 minus 2x times x all over the 1 plus x squared squared. So take a second and see if you can simplify that derivative down. This numerator here is 1 plus x squared minus 2x squared, so that's 1 minus x squared. And then we still got the 1 plus x squared squared. And then this 1 plus x over 1 plus x squared flips up into the numerator, 1 plus x squared over x. And what does that simplify to? Factor 1 minus x, 1 plus x over x times 1 plus x squared. Good or no?
Good.
All right. When is this equal to 0? If x is 1 or if x is negative 1. And when is it undefined?
When x is 0.
When x is 0, exactly. Okay, so of these three values, only one of those falls in this category where x is greater than 0. Right? So we have one critical value from all of that fun work. Okay? The critical value of x equals 1. Now let's see what happens if x is less than 0. Right, if x is less than 0, f prime of x should be the derivative of the natural log of this negative, which, what's that going to affect? All it's going to do is it's going to put a negative down here. And then when I take the derivative, it's also going to put a negative out in front of that derivative. So those two negatives are going to end up canceling each other out. Do you guys agree with that? Yeah or no?
Yeah.
Yeah. This, right, when we do 1 over this, it still has a negative here. And then when we take the derivative of a negative of something, it's just a negative of that thing. So those two negatives should cancel each other out. And we should end up with the exact same derivative, 1 minus x, 1 plus x, over x times 1 plus x squared, which should give us those same values, x equals 1, x equals negative 1, and x equals 0. The only one of which is on x less than 0 is negative 1. So we have two critical values. One is x equals 1, and one is x equals negative 1. So we're ready to make our sine chart. I promise we'll be done soon. And I'm putting 3 different values on my sine chart, and there's a reason why. I put 1 for negative 1, I put 1 for 1, but I'm also going to put 1 for 0, even though 0 wasn't a critical value. You should always, if there is a place where your original function has a discontinuity, always include that value on your sine chart as well, because things might also change at that x value. So now when we plug in something between, let's say, 0 and 1 into our derivative, and remember we got the same derivative for both of them, we plug in 0 to 1, like a half, this denominator is positive, and our numerator is positive, so we get a positive and we're increasing. And if we plug in something greater than 1, like 1,000, we've got a negative times a positive over a positive times a positive, giving us a negative. Everybody okay with the positive side of that? 0 to 1 and 1 to infinity? All right. And then if we go from negative 1 to 0 at negative a half, right? Let's say negative a half, that's going to give us a positive, and that's going to give us a negative and a positive. So we're going to have a negative and decrease. And something less than negative 1, like negative a million, is going to give us a, what's that going to give us? A positive, and a negative, and a negative, and a positive, which gives us a positive. So it looks like we should have a local max at negative 1 and at positive 1. And we should really quickly be able to go in and figure out what those values are. F of 1 and f of negative 1. You plug in 1 to this, you get 1 over 2, right? Half. And if you plug negative 1 in, you get negative 1 over 2, or negative a half. And then when you take the absolute value, it's still just a half. So we get natural log of a half and natural log of a half. And the preferred way to write these is natural log 1 minus natural log 2, or just negative natural log of 2. And so we have local and also absolute maxes at, of negative ln2 at x equals positive or negative 1. And we know that they're absolute maxes because if we look at this, we know that this height here is the same as this height here, and everything going away from it is always smaller than it. And I promise we're done, except that I'm going to just pull up the actual graph of this so we can see it. But anybody have any questions on that while I'm pulling up the graph? For those of you that decided not to leave early like some people did. And here's our graph, and here is our value at negative 1 negative ln2, and 1 negative ln2. And we are dropping down to a vertical asymptote at x equals 0, and everything on the left and on the right is below those values that we got. Everybody good? Any questions on that, or are we all right? All right, that's it.